Hi, and welcome to our new chapter here on classification. So after we have introduced the basic ingredients for machine learning from a quite high-level perspective, and after we've begun to formalize the first components of regression, and after we've looked at our first regression algorithms, here in this chapter I want to introduce the basic notation and a few simple algorithms for classification. You will figure out that the whole concept of ML applied to this different task doesn't really work that much differently. There are certain differences in how algorithms are constructed. You will see that notation becomes a little bit more tedious, but the general concept of empirical risk minimization and the general concept of learning a predictive function based on data stays very much the same. And later on you will also see that many algorithms nowadays can actually perform regression and classification, and the theoretical lens through which we analyze these things, the theoretical underpinning of the whole theoretical underpinning is very much the same. So there is not a large difference. Nevertheless, we are dedicating here an individual chapter to classification. I'll introduce to you that classification is basically supervised learning with categorical labels. So far, so simple. And in this introductory session here, I'll also introduce a couple of pieces of terminology. So what is binary classification? What is multi-class classification? Assuming you can already guess that, we'll just look at a couple of simple example tasks for classification before we move on to a more mathy session where I introduce more notation, more theoretical concepts, and then we'll begin to construct our first algorithms like logistic regression, discriminant analysis, or naive Bayes. Okay, so as I've already said, it's not a very big difference between classification and regression. So we are still learning functions. We are learning predictive functions, and we are learning predictive functions based on data. As we are in supervised learning, we'll assume that our data is labeled. And the major difference now is that our labels Y, they are not from R anymore, so they are not real values, but they are categorical measurements. So it can be something like, I don't know, here I've already used the iris task, which I will show you in detail a little bit later on. So we have these subspecies of flowers here, like Setosa or Virginica, or the class could be something like sick or healthy, or something like, your credit application is accepted or rejected, or something like this. And as in regression, we are now trying to build a predictive function which, based on feature data, tries to predict the label here for observations with high accuracy. I guess it's quite obvious there are tasks with two classes. And this is what we would call a binary task, and there are also tasks with more than two classes, and this is what we would call a multi-class task. So tasks are supposed, or classification tasks are supposed to have a finite number of classes, and these classes usually are not ordered. There are some exceptions, so you can actually have an order structure on the classes, like, I don't know, small, medium, or large, or something like that. But that would actually make it a specific task. So some people call this ordered classification or ordered regression. So this is like something in between classification and regression, and is usually handled specifically. And I don't want to discuss this here. So the basic assumption for regular classification is that there is a finite number of unordered classes. And here you would see some example of a binary classification task. So here we have used the SONA data set. So that's a simple, I'm not sure I want to call it a toy data set, but a simple example data set that's very often used in courses like this, or is even used more often here is this iris data set, which we will see in a few seconds in detail. So the data set here on the left-hand side, the SONA data set, has just two classes, which would make it a binary classification task, and the iris data set has three, so we'd call that multi-class. Some further examples, so I've already mentioned a couple of these. So credit risk prediction would be a further binary classification task, so based on potentially personal data, based on your prior transactions, we might want to predict what your risk for default is in a credit risk application. Spam detection is something that has been used in machine learning for years. Is an area where machine learning has been applied successfully since, I don't know, more than 20 or 30 years now. So based on textual features, we'd like to predict whether an email is spam or not. Churn prediction based on customer behavior. We might want to predict whether a customer would potentially leave a certain contract, or probably even more relevant than the 3 tasks above, so predictions in medical applications. So maybe you want to predict your predisposition for a specific illness based on genetic data. And here is exactly that scenario, stolen from this web diagnosis tool here under this given URL. So this would be some simple, I don't know, a prediction model which based on your very few personal attributes like your gender here, your age, and a rough description of your symptoms, apparently also whether you're pregnant or not, then lists a couple of conditions that hopefully with semi-high probability, I'm guessing this is not going to work that well if it's just based on these rough criteria here, whether a certain illness is more or less likely. And I guess you shouldn't only use a tool like that, but probably also if you're really feeling that bad, go to a doctor and have a proper diagnosis there. As a final example, we're going to take a look at the iris. So already mentioned that now a couple of times in the introductory slides. So this data set is actually quite famous. I guess it's covered in basically any book or course on machine learning. It's also now quite old. So this was originally collected by Ronald Fisher. And it is so well known that it has its own Wikipedia page. And Fisher collected this data set based on these 3 types of iris flowers. So there are 3 subspecies here of the iris flower. So the setosa, the versicolor, and the virginica. And Fisher designed that to, I guess he was just also interested in the topic as such, but he also collected the data set, or at least used it as a test case for linear discriminant analysis, which we will later on look at here also in this course. And the data set contains, in addition to 50 measurements on each of these 3 subspecies here, 4 numerical features. And Fisher was thinking about, is it potentially possible to measure the petal and sepal lengths here of these flowers, and then based on these measurements to predict the subspecies of the iris flower. So it is n times p data with 4 feature columns, which you can see here: sepal length, sepal width, petal length, and petal width. 1 categorical target column containing 3 classes. We have 150 observations, 50 per class, and pretty clean data. This is also what makes the data set a little bit, let's say, I don't know, dangerous in terms of, I don't know, extrapolating its properties to other data you might later on encounter in the wild. So in a certain sense, the data set is a little bit uncharacteristic in terms of its simpleness. So it's quite small. It is very clean. It has no missing values. All of the features are nicely distributed. There are no outliers. Data is pretty much nicely normally distributed and so on, which makes the data set very nice to use in courses like that to demonstrate basic concepts of machine learning and demonstrate basic concepts of algorithms, but it's not a very realistic one. And here's a final slide with some exploratory data analysis on the iris data set. So you can see a couple of, I don't know, 2D scatter plots here for all pairwise combinations of features. You can see how the histograms look like, or density plots for the marginals of the features. You can also see that if you take, for example, this feature here, that's nearly enough to discriminate the 3 classes by handcrafting a classification algorithm that will already work quite well. Or if you take a look at these 2D plots here, you can also see which combination works quite nicely. Yeah, so I don't know, maybe this here, just by eyeballing and with a pen, construct a classifier from that. But we also want to do this now automatically and numerically, and this is exactly the topic of the upcoming sessions.